Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Today we are going to start 14th lecture of discrete structures, CSC 102. In the previous lecture we have started set theory and we have discussed basic concepts of sets and operations on the sets. We have also discussed the memberships of elements and sets, inclusions, etc. And at the end we have discussed some the properties and operations on sets by using Venn diagrams. Today we continue the concepts of sets and we shall study the properties of sets and properties of empty sets, difference properties, set identities, and we will compare Boolean algebra and set theory, and at the end we shall discuss one or two puzzles which can be solved by using set theory. So in the last lecture we have discussed the memberships. If we have two sets x and y which are the subsets of a universal set U, then we repeat here some memberships of elements to their sets. So if x belongs to x union y, then x belongs to x, small x. Either x belongs to x or x belongs to y. So in union, in the last lecture we have also discussed that in union an element may belong to one of the two sets. It means this is basically, as compared to the logic, it's a disjunction property, you can say. And an element x which belongs to x intersection y, for this element it is necessary that x belongs to x and x belongs to y. So x must belongs to both sets x and y. And at number 3, if x belongs to x minus y, then x belongs to x and x must not belong to y. Similarly, if x belongs to x, then x doesn't belong to x complement. This sign is basically the sign of complement, or we can write xc. We have also discussed Cartesian product of two sets x and y, and in this case an ordered pair xy belongs to x cross y if and only if x belongs to x and y belongs to y. So a little bit revision of the previous lecture of the when an element belongs to the union, intersection, difference and complement of the sets. So now we discuss some properties of the sets. Here we discuss a theorem, inclusion of intersection. The first case is inclusion of intersection. For all sets A and B, A intersection B is subset of A. It is obvious because we can prove it by using Venn diagram, or we can see it by using Venn diagram also. But it is obvious that A intersection B is subset of A and A intersection B is subset of B. The second statement is inclusion in union. For all sets A, B, A is subset of A union B and B is subset of A union B. So we can easily prove this stuff. At number 3, transitive property of subsets. For all sets A, B and C, if A is subset of B, B is subset of C, then A is subset of C. So this is basically the transitive property of sets. We can prove all these properties, but here I shall prove only the first one, the A intersection B is subset of A. We shall prove only this property. The rest of properties can be proved similarly, and I left the other properties to be to prove for you as an exercise. So to prove A intersection B is subset of A, what we have to prove? So this is we have discussed it in the previous lecture, that to prove or to show that a set is a subset of another set, we have to prove that every element of first set is also the element of the second set. For example, if we have two sets U, and we have to prove it subset of V, then we have to prove that every element of U belongs to V also. So this is what we have to prove if we want to prove U is a subset of V. So to prove A intersection B is subset of A, we choose an arbitrary element of A intersection B, and we prove that that element belongs to A also. So this is what we have to prove. We suppose here X is an element of A intersection B. X is an arbitrary element. X can be any element of A intersection B. Now if we can prove that X belongs also to A, then we are done. Then we have proved that A intersection B is subset of A, because X is an arbitrary element, X is any element of A intersection B, and if we prove that any element of A intersection B belongs to A, then it means that all elements of A intersection B belongs to A also. So then we can say that A intersection B is subset of A. So here I have written to say that X is in A intersection B means that X is in A and X is in B. When an element belongs to intersection of two sets, then it is necessary for that element that it should belong to both sets. So this is what we have written here. So this allows you to complete the proof by deducing that in particular X belongs to A also. So as was to be shown, note that this deduction is just a special case of valid argument. This just a special case of valid argument, as we have discussed in the logic, that we can conclude that if P and Q is true, then P is also true, Q is also true, because if one of P and Q is false, then this whole conjunction will be false. So by using this argument also, we can deduce that A intersection B is subset of A. So thus we conclude that A intersection B is subset of A. We can also similarly prove that A intersection B is subset of B. So this is the proof of the first statement of this theorem. So we have proved that A intersection B is subset of A and A intersection B is subset of B. Similarly, we can prove the second and third. So I left these two for you as an exercise. The first identity of the sets is the commutative law. Now the commutative law says that if we have two sets A and B, then A union B is equal to B union A. It means that if we write A first or B second, or B first and A second, then it doesn't matter we write A first or B first, the resulting union of two sets will be same. We can interchange the order of sets. You can see here in union it will not affect the answer. So similarly similar is the case for the intersection. A intersection B is same as B intersection A. So this is called the commutative law of sets. As we have studied the commutative law of to proposition P or Q is basically logically equivalent to Q or P. So this is same as. we have studied in logic. The next identity is the associative law. So associative law states that if we have three sets A, B and C, and we take the union A, union B, union C, so we cannot take union of three sets at a time. First we take the union of two sets, and then we take the union of resulting set with the another set C. So we have to put brackets here around any two sets. So A union B, if we take A union B and then union C, or A union B union C, so this will be same as this union. So this is basically the associative law for set union. Similarly, there is a associative law for set intersection, which states that A intersection B intersection C, or A intersection B intersection C, these are basically two equal sets. Now the third property is the distributive law for sets. If we have three sets A union B intersection C, then this law states that this set is equal to A union B, A union C, and then intersection comes in the middle. So this is the distributive law for sets. Similarly, we can take the intersection out and union inside, means that this intersection is here and the union is here. So this states that A intersection B, A intersection C, and then we can write the union in the center. So this is basically the distributive law for any three sets. The next identity is A identity laws for all sets A. A union empty set is A, and A intersection universal set is basically A. So these are basically identity laws. Identity laws means if we take the union of A with the empty set, it will A will not be changed. Similarly, if we take the intersection of A with the universal set, we'll have the same set A. So there is no change in the original set A. Therefore these laws are called identity laws. The next is complement laws. A union A complement is always the universal set, and A intersection A complement is always empty set. Similarly, we have double complement law. If we take the complement of a complement set, then we will get the original set A. The next are the idempotent laws. A union A is equal to A, and A intersection A is A also. Universal bound laws. A union U is U, and A intersection phi is phi. So these are universal bound laws. Now we have to prove all these laws. So I prove only one or two laws, and then the remaining laws you can prove by yourself. So there are some other laws which are given here. De Morgan laws. De Morgan law states that if we take the union A union B whole complement, then it will convert as A complement, and union will be converted to intersection and B complement. So this is basically the De Morgan law of union, you can say. And if there is another De Morgan law in which we have intersection inside the complement. A intersection B complement is equal to A complement union B complement. We can prove all these laws, but and also we can prove, or we can see the equality here by using Venn diagrams. The next are absorption laws for all sets A and B. A union A intersection B and A intersection A union B. It means we have studied these laws also in logic. In the case of distributive laws, if we have two same sets in the distributive laws, then we have the set which comes two times. Here A comes two times. So here we have distributive law, but we have two sets same in the distributive law. As you can see in the distributive law here, we have A union B intersection C. So we have three different sets. A, B and C are three different sets. If we write A here instead of B, then the answer of this distributive law is straightforward A, because we have two same sets in the distributive laws. So this is basically given here. If in the distributive law any two sets are equivalent, then the resulting set will become A. Similarly, here we have A intersection A union B, then straightforward the resulting set will be equal to A. So these are basically absorption laws. The next is complement of U and phi. We know that the complement of universal set is empty set and the complement of empty set is universal set. So there is another identity which is set difference law. If we have two sets A and B, then A minus B is equal to A intersection B complement. So this we can also prove by direct method, or we have studied method of proofs by any appropriate method, and we can also prove it by using Venn diagrams. So now I give you the proof of some of the identities. For example, I give you the proof of distributive law for sets, especially this set. We shall prove this law, which is the distributive law, and we have to prove that left hand side is equal to right hand side. As in the previous lecture, I have told you one identity, that if we want to prove two sets to be equal, A is equal to B, then how we prove these two sets to be equal? We prove that A is subset of B and B is subset of A. If we can prove this, then we can conclude that A is equal to B. So this is what we shall prove here. First we prove that this left hand side is a subset of this, as you can see here, and then we shall prove that the right hand side is subset of left hand side. So how we prove that one set is subset of another set? We have discussed it earlier. We take an arbitrary element of the left hand side, this, any arbitrary element of this set, and then we prove that this element belongs also to this set, which is the right hand set. So we suppose that X belongs to the left hand side, this set A union B intersection C. Then we have to prove that X belongs to also A union B intersection A union C. So if X belongs to A union B intersection C, then by the definition of union, X belongs to A or X belongs to B intersection C. So now there are two cases. If X belongs to A, then what happens? And if X belongs to B intersection C, then what happens? So first case, we suppose that X belongs to A. Since X belongs to A, then X belongs to A union B, because for X to belong to A union B, it is sufficient that X belongs to A. By the definition of a union, also X belongs to A union C. By the definition of union, if X belongs to A union B and X belongs to A union C, then we can say that X belongs to the intersection of both these sets. Therefore, the left hand side A union B intersection C is subset of this right hand side in the first case. Now we consider the second case. We suppose that X belongs to B intersection C. Now, since X belongs to B intersection C, what does it mean? By the definition of intersection, X belongs to B and X belongs to C. By the definition of intersection, since X belongs to B and X belongs to C, then X belongs to A union B and X belongs to A union C, because X belongs to at least one set in these two sets, A and B, as similarly A and C. So therefore we can say that X belongs to A union B and intersection A union C, because here we have said that X belongs to A union B and X belongs to A union C. So therefore in both cases we can say that X belongs to A union B intersection A union C. So we have taken an arbitrary element of the left hand side. This arbitrary, it could be, I have told you that it could be any element. So any element of A union B intersection C belongs to this set. This means that this set is subset of this set. Now we suppose that this is equation 1. We have proved on the one side in this here. Now we are going to prove that the right hand side here, this is subset of this side. So how we can prove that this is subset of this? We choose an arbitrary element X which belongs to this, and then we prove that X belongs to this set. So this is sufficient for proving that this set is subset of this set. So we choose X belongs to A union B intersection A union C. Then by the definition of intersection, X belongs to A union B and X belongs to A union C. Now we have two cases in this case also. How? Consider the two cases, X belongs to A and X doesn't belong to A. Why? Because here, if we are succeeded to prove that X belongs to A, then we are done. How? If X belongs to A, and here we have union A union B intersection C. If X belongs to A, then X belongs to whole this set, because there is a union between A and B intersection C. So we can say that if X belongs to A, this implies X belongs to A union B intersection A union B intersection C. So X belongs to this set if X belongs to A. So that's why we suppose that we consider the two cases, if X belongs to A and if X doesn't belong to A. So in the first case, we suppose that X belongs to A. Here, if X belongs to A, then we can conclude that X belongs to this set, and by the definition of union, then we can say that A union B is subset of this set. In the second case, when X doesn't belong to A, and then we have that X belongs to A union B, because we have supposed here that X belongs to this set, then X belongs to A union B. So if X doesn't belong to A and we know that X belongs to A union B, what does it mean? It means that X belongs to B. If X belongs to B, yes, and similarly for this case, X belongs to A union C. Since X belongs to A union C and we know that X doesn't belong to A, this means that X belongs to C. So if x belongs to C, and we have also proved here that x belongs to B. Here we have proved that x belongs to C. It means that x belongs to B and x belongs to C. If x belongs to B and x belongs to C, then by definition of intersection, x belongs to B intersection C. Now if x belongs to B intersection C, then x belongs to A union B intersection C. So in both cases we have proved that x belongs to B intersection B union B, A union B intersection C. So we have chosen an arbitrary element of this set, and we have proved that that element belongs to this set. This means that this set is subset of this set. Now this is equation 2. In equation 1 we have proved that this set is subset of this set, and in equation 2 we have proved that this is subset of this. Now we can conclude by the definition that if x belongs to if A is subset of B and B is subset of A, then we can say that A is equal to B. So by using this identity or property, you can say this left hand side is equal to right hand side. So this is basically the distributive law for sets, and we have proved it. We can similarly prove the other identities which we have discussed here: commutative law, associative law, distributive law, identity, complement laws, and all other laws we can prove similarly. So we prove another law here, and then we will move forward. This law is very important in set theory, so we discuss the proof of this law here. Prove that for all sets A and B, A union B whole complement is equal to A complement intersection B complement. So this is De Morgan's law for sets. So to prove this set is equal to this set, what we do? We do the same procedure as we have done in the previous proof. We choose an arbitrary element of the left hand side. X belongs to A union B whole complement, and then we prove that this X also belongs to this right hand side. So if X belongs to A union B whole complement, this means that X doesn't belongs to A union B, because X belongs to A union B whole complement. This means that X doesn't belongs to A union B. But to belongs to A union B means that it is false that X is in A or X is in B. It means that X doesn't belongs to A, and or X is not belongs to B. So if X doesn't belongs to A and X or X doesn't belongs to B, then we can say that X belongs to A complement and X belongs to B complement. Here we have or, here we have and. So this is basically, as we have studied in logic, De Morgan's law. This implies that the negation of this is what? If X doesn't belongs to A union B, what is the negation of this? X belongs to A complement and X belongs to B complement. This is what I have written here, that if X doesn't belongs to A union B, it means X doesn't belongs to A or X doesn't belongs to B. And the negation of this is basically, as we have discussed in logic, X belongs to A complement and X belongs to B complement. If this is true, then X belongs to A complement intersection B complement. If this is true, then by definition of intersection we can write this. So this is what we have to prove. So we can say that this side is subset of the right hand side. Now one inclusion has been proved. Now we are going to prove the converse of this case. Means that we are going to prove that this is subset of this set. Now what we do, if we do the same process, we choose an arbitrary x which belongs to this set, and here we have intersection. By the definition of intersection, we can say that x belongs to A complement and x belongs to B complement. And by the definition of complement, if x belongs to A complement, then x doesn't belongs to A and x doesn't belongs to B by the same argument. In other words, x is not in A and x is not in B. Then what does it mean? It means that x is not in the A union B, because x is not in both A and B, then x obviously doesn't belongs to A union B. If x doesn't belongs to A union B, then x must belongs to A union B complement. So this is what we have to prove. Then we can say that this side is the subset of this side. So we are done basically. In here we have proved that if we say this equation 1 and this equation 2, then by equation 1 and 2 we can say that A union B whole complement is equal to A complement intersection B complement. So this is De Morgan's law. So we have proved two laws, distributive law and De Morgan law, for the sets. The rest of the proofs, the rest of the identities, you can prove yourself. So these are very, I hope these are very simple now for you. Now we move further and we discuss some properties of the empty sets. Now by the definition of empty set, a set which contains no element basically is called an empty set. So if we have a theorem here, if E is an empty set with no element, that is E is empty set and A is any set, then E is subset of A. What does mean this theorem, or what does this theorem says? It says that empty set is a subset of every set which is not empty. So this is what we are going to prove. So we shall prove this theorem by the method of contradiction. So here we have to prove that E is subset of A is any set. We have to prove this. We suppose that E is not subset of A. Here what we have supposed here, we suppose not means E is not subset of A. So we have we use here method of contradiction, and by the definition of proofs by contradiction, we suppose that the conclusion is false here. Then we move, now we do some steps and we should arrive at some contradiction by the method of contradiction. So we move further here. Suppose there so here we suppose that E is not subset of A, then by the definition, when a set is not subset of another set, when it happens, you know it, in the previous lecture we have observed such type of things. If E is not subset of A, then there exists at least one element in then there exists at least one element in E which doesn't belongs to A. So that's why E is not subset of A. But here suppose there exists a set E with no elements and a set A such that E is not subset of A. You can write it here. then there would be an element of E that is not an element of A. This is what I have told you now. But we know that there is no element in E by definition, by the hypothesis here. By the hypothesis here, this is basically the P of x, and this is what? This is Q of x in the universal conditional statement. If P of x, then Q of x. So we have supposed that the Q of x is false here. But hypothesis is always true in the universal conditional statements. We suppose them always true. Then in the hypothesis we have that E is a set with no elements. But there can be no such element since E has no elements. So this is contradiction to the supposition that E has no element. So we can say that our supposition was wrong, that E is not subset of A. Then what will be true? The Q of x will be true, means E is subset of A. So we conclude that this theorem is true, that every empty set is a subset of a non-empty, any non-empty set. So this is what we have proved for all empty sets, for all sets. The next is the uniqueness of the empty set. There is only one set with no elements. So we have to prove that there is only one set with no elements. So this we again prove by the method of you can say uniqueness. We always prove like this. If we have to prove anything is unique, then we suppose that there are two things. We suppose that that thing is not unique. There exist two such things. We suppose it. So here we have to prove that there is only one set with no elements. So to prove this statement, we follow this procedure. We suppose that this is not unique. So we suppose that E1 and E2 are both sets with no elements. Then E is subset of E2. By the previous theorem, we have previous theorem we have supposed that we have proved that empty set is a subset of any set A. So if E1 is the set with no elements, then E1 is subset of E2. So this is true, since E1 has no elements. Also E2 has no elements, then E2 is subset of E1, since E2 has no elements. So we have proved that E1 is subset of E2 and E2 is subset of E1. What does it mean? It means that E1 is equal to E2. So what we have supposed that there are two such sets is false. Actually they both are equal. So what does it mean? It means that this statement is true. There is only one set with no elements. So another statement which we have to prove, a set with no element is a subset of every set. This is what we have proved in this theorem, I think. So there is no need to prove this, or you can see it yourself. So next we have to prove this conditional statement. This is basically a property of sets. Prove that for all sets A and B, A, B and C, if A is subset of B and B is subset of C complement, then A intersection C is phi. So what is the proof of this universal conditional statement? Suppose A, B and C are any sets such that A is subset of B and B is subset of C complement. So this is what we have supposed, that this is basically the hypothesis of conditional statement. This is the conclusion. So we suppose that the hypothesis is true. So we must show that Q of x is true, means A intersection C is phi basically. Now suppose not. Here we are again using the method of contradiction. We suppose that A intersection C is not empty. That is, suppose there is an element X belongs to A intersection C. If A intersection C is not empty, then there must be some element X which belongs to A intersection C. So if X belongs to A intersection C, then X belongs to A and X belongs to C. If X belongs to A, and we also know that A is subset of B and B is subset of C complement. So if X belongs to A and A is subset of B, then X belongs to B also, because A is subset of B by the definition of subset. Also, here we have supposed that B is subset of C complement. It means that B is subset of C complement, because X belongs to B here and X belongs to C. And also, since this B is subset of C complement, then X belongs to C complement, because A is subset of B and X belongs to B. And here we have supposed that X belongs to B is subset of C complement. If X belongs to B, then X belongs to C complement by the definition of subset again. So it follows by the definition of complement that here we have shown that X belongs to C complement, then X doesn't belongs to C by the definition of complement. So here we have that X belongs to C, and here we have that X doesn't belongs to C. So X belongs to C and X doesn't belongs to C. This is basically a contradiction, which is a contradiction because at one place we say that X belongs to C, and at another place we have proved that X belongs to C complement. So this is a contradiction. There is a confusion, you can say. So if there is a contradiction, then where is the problem? The problem is in our supposition. What we have supposed, actually we have supposed the wrong thing, that A intersection C is not phi. Then if our supposition is wrong, then what is true? This is basically Q of X is true. This is what the method of contradiction we have already discussed in detail. So we have proved this theorem also, which is an important property for sets. Now finding a counterexample for identities. So if we are unable to prove a set identity, then how can we find a counterexample for the identities? For example, we have to prove that this is equal to this, and we use direct method, we use indirect methods, method of contradiction, method of contrapositive, many other methods, and we are unable to prove that this left hand side is equal to right hand side. Then what we do, we find a counterexample whether this identity is actually true for all these sets or not. So we are going to find a counterexample for this identity, that this identity is not true. So if we suppose that A is a set which contains 1, 2, 3, so 1, 2, 4, 5, B is a set which contains 2, 3, 5, 6, C is a set which contains 4, 5, 6, 7, then we choose some particular sets A, B, C. Now we calculate the left hand side, then we calculate the right hand side, and then we see whether these two sides are equal or not. So we calculate A minus B here. A minus B is basically, we subtracted 2, we subtracted 5, so we get 1 and 4. We calculated B and C, B minus C, so we subtract 5 and 6, we get 2, 3. We calculated A minus C, which is 1, 2, so we take the union of these two, A minus B and B minus C. The union of this is 1, 2, 3, 4. Now A minus C is 1, 2. So whether this set and this set are equal? No, these two sets are not equal. So in general, this identity is not true. So this is how we can find counterexample. This is another counterexample for the same identity, but it means that it is not necessary that there is only one example which dissatisfy the above equality. You can find many counterexamples to prove that this identity is not equal. But in some cases there may be a unique counterexample which dissatisfy the equality. But in normal cases there are several counterexamples which dissatisfy the given identity or equality. So if we take a is equal to 5, b is equal to 3, c is equal to 5, then a minus b is 5, b minus c is 3, a minus c is 5, and hence the union of these two is basically 3, and a minus c is 5. So these two sets, phi and this set, are not equal. Therefore this equality is not true. So now, deriving a set difference property, this is also another important property of in sets. This states that if we have three sets a, b and c, then a union b minus c is a minus c union b minus c. So union comes in between here. So we have to prove this identity. We use some set identities to prove this. So we take the left hand side, a union b minus c. So by using this identity which we have proved here, the last identity which we have studied here, this a minus b is equal to a intersection b complement. So using set difference law here, we can write a union b minus c is equal to a union b intersection c complement by using set difference law. And then by using commutative law, we can write c complement intersection a union b. So now, using the distributive laws, this is c complement intersection a, c complement intersection a, and c complement intersection b, and the union comes here. Now we can again use the commutative law here. A comes here, c complement comes here, b comes here, c complement comes here. Now again, by using the set difference law, we can write a minus c union b minus c. So this is what we have to prove. So by taking left hand side and using set identities, we have proved this set identity, set difference property. Another property for the sets in which we have to prove that a minus a intersection b is equal to a minus b. So this is another important property for this set identity. We take the left hand side and we use the same process to prove this property. Suppose a and b are in two sets, then we take the left hand side here, and this is basically equal to a intersection b whole complement by using set difference law. Now by using De Morgan's law, we can use De Morgan's law here, and this intersection will become union, and we take the a complement and b complement. This here we have complement. So we obtain a intersection a complement union b complement. By using distributive law, we can write a intersection a complement union a intersection b complement. So a intersection a complement, this is basically by complement law, this is the empty set, and then here we have a intersection b complement. If we take the union of this set with empty, we get the same set. So Here, by using set difference law, we can write A intersection B complement is equal to A minus B, which is the right hand side, which was required here. So again, by using set identities, we can prove these this set identity. Now we compare these identities with the identities of Boolean algebra or logical equivalence. We have studied some identities in logical equivalences, so they have a lot of resemblance between them. Here on the right hand side we have set properties, here we have properties of logical equivalences. Here we have this law, the commutative law for disjunction and conjunction. Here we have commutative law for union and intersection. Here we have distributive laws for conjunction and disjunction, associative laws. Here we have associative laws for conjunction and disjunction. Here we have same associative laws for union and intersection. Here we have distributive laws for the conjunction and disjunction. Here we have the same distributive laws for sets. Here all laws are for propositions. Here on the right hand side all laws are for the sets. Here we have this law P or C is equal to P, where C is the contradiction. Here in place of contradiction we have empty set, and in place of proposition we have set. So all these properties, the other properties are also comparable. These are properties for the propositions which we have studied in logic, and these are the properties for the set. Actually these all properties have same meanings in logic and in sets, but the context is different. In the end, I would like to discuss a barber puzzle with you. There is a town, and in that town there is a male barber who shaves all those men, only those men who do not shave themselves. So I prefer to discuss this puzzle in Urdu with you, because in Urdu we can explain or understand better. एक कस्बे में एक नाई रहता था जो कि एक मेल नाई था, ठीक है। वो सिर्फ उन लोगों की शेव करता था जो खुद शेव नहीं करते। डेफिनेटली सिर्फ उन्हीं लोगों की शेव कर सकता है, जो खुद शेव कर लेंगे वो तो नाई के पास नहीं जाएंगे। सो नाई जो है सिर्फ उन लोगों की शेव करता था जो खुद शेव नहीं करते थे। ओनली दोज मैन हु डू नॉट शेव देमसेल्फ। नाउ द क्वेश्चन इज, क्या वो बार्बर जो है अपनी शेव खुद करता था? सो नाउ वी हैव टू आंसर दिस क्वेश्चन. सो नीदर yes nor no. We cannot say yes and we cannot say no because this puzzle doesn't have any solution. So I'll tell you also this. मैं आपको solution भी आखिर में बताऊंगा कि अगर तो नाई अपनी शेव नहीं करता, there are two classes, दो क्लासेस हैं, दो ग्रुप्स हैं उस टाउन में। एक वो लोग हैं जो कि शेव खुद नहीं करते और एक वो लोग हैं जो शेव खुद करते हैं। अगर तो नाई अपनी शेव खुद करता है तो इसका क्या मतलब है कि वो उस बंदे की शेव कर रहा है जो शेव खुद करता है। सो इस पे थोड़ा सा मतलब गौर करना है आप लोगों ने कि नाई सिर्फ उन लोगों की शेव करता है जो खुद शेव नहीं करते। अब सवाल ये है कि नाई अपनी शेव खुद करता है या नहीं। सो उस टाउन में दो किस्म के लोग रहते हैं, एक तो वो जो अपनी शेव नहीं करते, एक वो लोग हैं जो अपनी शेव करते हैं। अगर नाई अपनी शेव खुद नहीं करता तो वो उस कैटेगरी में, उस ग्रुप में आएगा जो कि अपनी शेव नहीं करते। तो इसका मतलब है कि शायद नाई उस टाउन में कोई और नाई भी नहीं है, सिर्फ एक ही नाई है, तो फिर नाई अपनी शेव किससे करवाएगा। तो यहाँ पे इसका मतलब है कि नाई अपनी शेव नहीं करता, ये हम नहीं कह सकते। अगर नाई अपनी शेव खुद करता है तो वो उस ग्रुप में लाई करेगा, उन लोगों के ग्रुप में लाई करेगा कि जो लोग अपनी शेव खुद करते हैं। इसका मतलब ये है कि नाई दूसरों की शेव नहीं कर सकता फिर, क्योंकि नाई सिर्फ उन लोगों की शेव करता है जो अपनी शेव खुद नहीं करते। सो देयर इज नो आंसर टू दिस पजल, बट वी कैन से दैट एक तो ये सोल्यूशन है इसका कि नाई ने दाढ़ी रखी हो, इसका मतलब है कि नाई अपनी शेव खुद नहीं करता, तो वो उन लोगों की शेव करता है जो कि अपनी शेव नहीं करते। या तो फिर नाई मेल ना हो, लड़की हो, वो अपनी शेव नहीं करता तो दूसरों की कर सकता है। लेकिन यहाँ पे ये मेंशन है कि मेल बार्बर है, फीमेल बार्बर नहीं है। सो यू कैन रीड दिस स्टफ and you will better understand this barber puzzle, which is also given in the books of discrete mathematics of Susanna and Rosen. You can also consult these books to understand better this puzzle. So for today it is enough, I think, and what we have studied we summarize here. First of all, we have studied some properties of sets, set identities, which are commutative laws, distributive laws, and there were some other properties of sets. We have studied the properties of empty sets, and we have proved some difference properties of the sets by using set identities, or you can say laws of sets. And then we have compared Boolean algebra, the properties of logic, the laws of logic with the laws of set theory, because there is almost, you can say, there is much resemblance between the laws of set theory and laws of logic. And at the end we have discussed a barber puzzle. So in the next lecture we shall start, inshallah, the relations. For till that, Allah Hafiz.